The next thing to talk about is radioactivity. In 1895, X-rays were discovered, and the following year, naturally occurring radioactivity was discovered. A Frenchman named Becquerel made the observation that if he placed a uranium ore called pitchblende on top of a photographic film, which was surrounded by opaque black paper, he would get an image of the rock of ore that he had placed on the opaque paper when he developed the film. So this illustrates that in order to study a phenomenon like radioactivity, you need to have the right tool. And the right tool, in this case, was photographic film, which had been developed earlier in the 19th century. People had been living in the presence of radiation for as long as there have been people. But we have no natural built-in means of detecting radiation. So we needed a tool, we needed a technology, and that technology was chemical photography. In chemical photography, a fine suspension of crystals of a silver halide, like silver bromide, is spread onto a film base. And this material can then be exposed to light. When it is, the photons of light, or of X-rays or other kinds of radioactivity in this case, will cause just the very beginning of a chemical reaction in some of those grains of silver halide. If you then treat the silver halide with a reducing agent called a developer, it will permit the chemical reaction to spread in the grains where it was started by light. But the grains which were not exposed to light won't show any chemical reaction. They will remain as silver halide. The ones exposed to light will be converted to metallic silver. And then when you stop the development, you use a fixing solution which washes out the unconverted silver halide and leaves the silver, and you have an image. This was the basis of all photography for a long time. Now, of course, we use electronic photography for the most part. But the presence of that technology made it possible to detect what had been there all along, which was radioactivity. When people studied radioactivity a little more, such as by passing a beam of radioactivity from radium between electrically charged plates or within a magnetic field, they found that the beam was actually made up of 3 different kinds of radioactivity. There was a kind that had a positive charge. Those were named for the first letter of the Greek alphabet, alpha. The alpha particles turned out later to be the nuclei of helium atoms. There was a kind that had a negative charge, and those particles, which were named beta, were in fact electrons. And there was a third kind of radiation that wasn't bent at all by an electric or magnetic field, and those were called gamma rays. And it turns out that they are photons of light, but a much more energetic light than we can see. They're actually beyond X-rays. Remember, I told you about the Rutherford experiment in which he subjected gold foils to bombardment by alpha particles, and these alpha particles came from a radioactive material like radium. It was this experiment which established the existence of the atomic nucleus. At the time radiation was first discovered, nobody knew that nuclei had atoms. I'm sorry, that atoms had nuclei. And so it was just something that came out of the atom as far as they were concerned. It was only later, after the Rutherford experiment, that people understood that these radioactive emanations of atoms came from their nuclei, by and large. There are a couple of exceptions to that, but by and large, from the nuclei. And so these nuclear, what should we call them, disintegration products, breakdown products, are what made it possible to probe the nucleus a little bit. This chart behind me is a chart of the nuclides. It's something like a periodic table, but instead of having one square for each element, it has one row across the table for each element, and the individual squares are for different isotopes of the same element. That means they have the same number of protons, the same atomic number, the same positive charge on the nucleus, but different numbers of neutrons in the nucleus. Some have just the right amount, and so they're indicated in black as being stable. Others have too many neutrons, and they're indicated in this color behind me. And others have not enough neutrons, too many protons, and they're indicated by this color. The way to think of this graph is think of the black areas as a river running through a valley. And on either side of the river are steep cliff faces. And the isotopes up on either one of these cliff faces want to attain stability. To do it, they have to come down toward the river. In the process of coming down toward the river, they have to give up some of their excess particles and their excess energy, and that is radioactivity.